fun and related to your quantum stuff with Waleed. So, you know, all the quantum gates and things like that you learned about with Waleed. I decided that for fun this weekend I would write a. We're doing some research for Space Force and NSF grant, and so I needed to get some inner knowledge of a couple of quantum things that we're working with. So I decided it'd be fun just to write my own quantum computer simulator, you know, like as one does on the weekends. So, and I did it all inside of VR and all using online GDB. So, yeah, so I mean, I can generate qubits. I can put them through a quantum gate. So, you know, if you remember when you first get a qubit, it's in a 0-0 state. So if I run that, there's the 0 in the 1 in the 0's place, the 0 in the 1's place. Put it through an X gate right here, which flips it. That puts it into a 0 in the 0 place, a 1 in the 1's place. I can throw it through the Hadamard gate. Remember the one that kind of throws it into superposition? And you'll see a superposition state now. In theory. Of course. Lippmann quantum simulator. All right, here's my superposition state. Yeah, so that's in superposition from a quantum 1. Remember, all quantum gates are reversible. So if I run it through a H gate again, I get back to the 1 state, so on and so forth. So that was kind of fun. And so, I mean, the reason I show this is the kind of stuff, once you get programming as a skill set, you can just sit down and say, hey, I want to explore something. And one thing that I'm a big advocate of is if you are able to implement it, you learn a lot about what's happening under the hood. You know, so really a majority of the stuff back here is just linear algebra, you know, matrix multiplication stuff, and something called tensor multiplication that Wally probably talked about, which is the, you know, and it's actually very related to where we're going here with this homework with fractions. As interestingly enough, you wouldn't think they would be related. But when you, so when Wally was here, you worked with a language called Qiskit, right? That IBM language. So this is like what I wrote, like a competitor to Qiskit, I guess. It's probably only 80% of the functionality so far, but it's kind of does the same thing. But what's interesting with quantum is if you try to write a, let me make sure I'm recording. Yeah, I am. If you try to create a quantum simulator on classical hardware, our modern computers are kind of limited at right around like 23, 24 qubits or something like that. And it has to do with the amount of computational power we have. You know, we talked about in the first week or two of class, you know, that, oh, we have more memory than any of us will ever need today, right? Unless we run into some very mathy issue where we actually need more memory than that. And a quantum simulator ends up being one of those, because things grow exponentially. So the idea is if you have 2 qubits and you entangle them, doesn't matter what a qubit is or anything like that, you need now a matrix. So a qubit stores 2 numbers, right? It's a vector with 2 numbers in it. If you have 2 qubits, each with 2 numbers, and you entangle them, whatever that means, you end up having to have a 4 vector to hold the shared state. of all those things. So you need your vector size just doubled in size, because now you need to keep track of a linked state between two qubits. Well, if you add a third, now you need 8. Then you need 16. Then you need 32. Kind of goes back to the idea. How many of you have heard that thing of, what if somebody gave you a penny a day but doubled it every single day? At the end of a month, you'd have $1 zillion. It's that type of thing where you think about, okay, well, so storing two numbers in a matrix, in an array, two numbers in an array, not a big deal, right? How big's a number? Our integers are 32 bits. So we're going to take 64 bits of stuff. Since I'm storing, floating point values, I can use a double. A double is like 96 bits, or a float is 64 bits of data. So if you only store two doubles or two floats, let's say, you're using 128 bits of data. Well, our computers today have 16 gigabytes of RAM or 32 gigabytes of RAM. So that feels like, oh, it's plenty, right? Well, what if you have 2 to the 24th? So if I wanted to represent 24 qubits and enable those to be entangled, I wanted my quantum simulator to support entangling these qubits, I would need a single array with 16,777,216 buckets in it. And each of those buckets will be taking up 64 bits of space. Divided by 8 is bytes. Divided by 1,024 is kilobytes. Divided by 1,024 is megabytes. Here we'll do divided by 1,024, that's gigabytes. That's 0.125 gigabytes. Not so bad. Well, let's bump this to 28 qubits. Now we're at 2 gigabytes. Let's bump this to 30 qubits. We're at 8. Let's go to 40 qubits. Now we're at 8 terabytes of memory. So where are we at here? So that's 2 terabytes of memory. So 38 qubits would run on some of our giant server type computers that you can buy a computer that can be expandable to enough memory to put 2 terabytes of memory into it, but none of our personal computers, right? Drop that to 35. Now we're at 256 gigabytes of memory. 34 is 128 gigabytes of memory. 33 is 64 gigabytes of memory. Anybody in here have 64 gigabytes of memory in their computer?
That's
32 is 32 gigabytes of memory. So anybody have 32 gigabytes of memory? Okay, a couple people. So we're starting to jump down into reality, right? In terms of what you could potentially store on your computer. Yet, one of the things Wally would have talked about, and I know a lot of that stuff was kind of pie in the sky, confusing type stuff, but one of the things he would have talked about is this famous algorithm called Shor's algorithm. Remember him mentioning that? Anybody remember what Shor's algorithm is used for? So whenever you are on a website and you put in your credit card information and you hit send, you see that little lockbox in the bottom left-hand corner? That's encrypting your credit card information so that people on the internet can't see it, right? And that's using a very specific kind of encryption. Anybody know the type of encryption it uses? It's based on a fairly simple but interesting math problem. It's called RSA, named after the people who created it. And RSA, the way that works is you take 2 relatively large prime numbers. And believe me when I say this is related to what we're talking about. All right, we're not just jumping back into quantum. All right, so the way RSA works is you take 2 large prime numbers and you multiply them together, so you get a big number, right? So RSA security is based on how difficult it is to, from that big number, factor those 2 original large primes out of it. Figure out what numbers were multiplied together to give you this giant number. So the prime factorization of large numbers is considered to be very, very difficult from a time perspective. So most of our higher end security today uses 2 gigabit RSA. So that means it uses 2048 individual zeros and ones as the basis for the size of the value that you get as a result of multiplying 2 large primes together. All right, so you get some gigantic value. So you would imagine that as that value gets bigger and bigger, the difficulty in factoring the primes out of it becomes more and more ridiculous, right? And the reality is the ridiculousness by today's computing power is right around 3 trillion years. Okay, so do you feel pretty safe when you put your credit card information into a website and hit send when you got the little lockbox? If on average it would take somebody 3 trillion years to crack your credit card, you feel like that's reasonably secure, right? All right, so but with quantum, 3 trillion years just turned into what would you guess? If quantum was able to solve this, go ahead. Yeah, it's like 5 or 10 minutes. That becomes problematic. If somebody could have the encrypted version of your credit card and in 5 or 10 minutes could start buying crap, that would be bad, right? All right, so Shor's algorithm is a quantum-based algorithm to factor large primes out of that big number. But the reality is in order to crack 2048-bit or 2 gigabit RSA encryption, you would need a quantum computer with, I think it's 4,099 qubits, a physical quantum computer with 4,099 qubits. Google right now has a physical quantum computer with 4,000 qubits. I mean, we are knocking on the door, right? And each year, if you go back and you look at the last several years and you've seen how many physical qubits they've been able to build machines with, it keeps multiplying multiple times, right? So the chances of us having a 10,000 qubit machine next year is high based on what we've had before. Now, it is difficult to build quantum computers, but we have these super, super, super rich companies working on it, right? Google, IBM, Microsoft. We got a couple of startup companies that are in it that get funding from big hedge funds and things like that. So this isn't something that, we're going to go and work on in our basement. None of us have freezers that can get down to like zero Kelvin. Because that's the problem with quantum is we have to hold it at super, super cold temperatures so that the qubits don't lose stability, all this jazz. So the idea is we almost have a physical quantum computer with we already do have one with 4,000 qubits. Well, if we were going to write a simulator on your normal computer hardware, you're not going to get the speed of quantum, but you're simulating the math behind quantum. So if I had a 4,000 qubit computer, notice it can no longer do the math. If you go on to Google, it just gives you a number that says undefined, right? But you can probably open up things like Wolfram Alpha and things like that and get the actual number that's like 50 pages long or something like that. It's some gigantic amount of RAM that you would need, probably more RAM than has ever existed in the history of humankind. Okay, so that's not something that we're going to be able to simulate on our computers because of the amount of memory it takes. Well, that's kind of the antithesis of what we talked about week 1 of class when we said, oh, when you have 16, 32 gigabytes of RAM, you never need more than that for a majority of the problems, right? But every now and then you run into something like this that has, a complexity or a numeric complexity, a computational complexity, or some things are a time complexity, which we're going to be looking at with fractions. That actually cause legitimate problems in our computers. So just kind of a fascinating thing. So one of the things we're working on with Space Force and NSA is a distributed tensor model where we can store parts of that shared state of qubits in the cloud, possibly on blockchain, so that we don't need to rely on physical computers with memory, individual memory. We can rely on something else. It's not going to allow us to get to 4,000 qubits, but maybe it'll allow us to build simulators with 100 qubits or something like that, which will allow us to test more quantum algorithms. Because Shor's algorithm has only been tested on physical quantum computers for much smaller keys and tested on classical computers running quantum simulators on basically, like, 16-bit RSA encryption. But mathematically, it works, which makes it pretty scary that we're knocking on the door of having something that can crack 2 gigabit RSA. So what's the initial thing we can do as humans to stall the problem? Jump to 3 gigabit RSA, 4 gigabit RSA, 6 gigabit RSA. We're still in the realm of that isn't overly inconvenient, but basically you're just keeping, just 10 steps in front of where the quantum computers are chasing you. And eventually you get to the point where encrypting our credit cards with RSA will be so slow because we've just made the keys so big that it no longer will be a viable encryption algorithm, right? It's like, okay, well, fine, it'll take, by normal computer standards, a trillion years to crack this, but it also takes a week after we hit send to send our credit card for it to get encrypted. You probably want your purchase to go through more quickly than that, right? So it becomes a very kind of interesting problem. But the shared state of entangled qubits is a very interesting problem that is very similar to what we're going to be looking at with fractions. So you can really see the difference. So when you hear qubits in quantum, you think crazy mathy stuff, hard to understand, right? You think of fractions, you think third grade math, right? When you first learned about fractions, this isn't super hard stuff, right? But we're going to see pretty quickly, we're going to write a program using our fractions. And the only thing we're going to be working on is reducing a fraction. And we're going to see that we can write that program and it will take too long to run. Probably would take something like a week to run. And then we're going to look at a known algorithm for making that better. And it'll go from taking a week to run to taking like a second to run. Just using a famous algorithm called Euclid's algorithm. Euclid's algorithm is to find the largest common divisor of two numbers. So kind of similar to RSA, kind of in the same ballpark. But in any case, kind of cool stuff, I guess, I think. Let's see. Is this where we left off? Yeah. All right. So homework for today. So we are going to, again, this kind of gets back to this idea of we're using our current tools that we have in our programming toolbox to start thinking about how can I use programming to represent different things. So similarly to I said, I wrote some stuff to represent a qubit. Now we want to say, well, how could I represent a fraction inside of my program, right? And based on what we know right this second, we're going to say, well, we're going to represent fractions using an array with two things in it. Bucket 0 will be the numerator, bucket 1 will be the denominator. Make sense? Okay. So let's start off with that. I'm just going to dump everything. I'll leave my random number generator thing. We'll dump all that. We'll just assume it wasn't important. All right. Now, let's go ahead and create a couple of fractions. So we're going to create a int array. We'll call this guy F1. And this is going to be an int array that's holding two numbers. And we'll create an int array F2, and this is going to be an int array also holding two numbers. So we'll say F at bucket 0 is equal to a 1. F at bucket 1 is equal to a 2. And it's F1 actually, right? F1, F1. And we have F2 at bucket 0 is equal to 3. F2 at bucket 1 is equal to 4. So F1 effectively, by our definition, holds the fraction 1/2, right? And F2, by our definition, holds the fraction 3/4. Now, keep in mind, we've just decided that we want to be able to represent fractions in our program, and using only the tools we have available to us, I need to have a way of keeping track of a numerator and a denominator, but have it associated with a single variable name. So we're going to do this as a 2-bucket array. There probably is a better way of doing it, but that's what we have available to us right now. Make sense? All right. So this isn't that fraction. This is built into language or anything like this. This is just us playing with the Legos we have available and figuring out how could we keep track of a numerator and denominator of a fraction. Make sense? All right. So now one of the things, let's review the assignment, was supposed to create fraction. So we want to create a function called create fraction that takes 2 integers as parameters and returns a 2-element array with the value of those fractions. So let's look at that. So we'll go ahead and prototype it here. So we're going to be returning an int pointer. We're going to call this guy create fraction. And that's a hard word to spell, at least for me. He used to do that, and then I like the problem with it. I would normally probably do that myself or call it num and denom or something like that. I'm a big advocate of making sure our variable names have meaningful names. So the reality is even though internally I would probably tend to use shorter variable names in this really drives that point home of using names that are completely understandable, right? First element is the numerator, second element is the denominator, even though I can't spell it very well. But that's why we have copy and paste. But you're right. We probably could have called it num and denom, and that I think all of us would have been able to follow what that was. But in any case, I'm purposely being extra verbose when it comes to it to drive that point home that it's important to have meaningful variable names. All right, so we're going to go ahead and write create fraction. So we're basically going to do exactly what we did up here. So I'll go ahead and put a fraction in there. We'll say F1 at bucket 0 is equal to numerator. F1 at bucket 1 is equal to denominator. And then we will return F1. So now I can do something like int pointer F1 is equal to create fraction of 1/2. Int pointer F2 is create fraction of 3/4. So we've just abstracted it. Abstraction is just simplification. It's the same math as we just wrote inside of main. We just shoved it inside of a function called create fraction that now I can just throw 2 numbers at, and it will do the magic and hand me back the array. Okay. Do we also have like a display fraction? Let me do display fraction first so we can do some testing, right? So display fraction, that's going to return nothing because we're not actually returning anything. We're just putting something on the screen, right? We'll call this guy display fraction. And it's going to take an int pointer fraction as a parameter. Oops, we're going to implement it later on. And actually, I would probably call this the fraction. That tends to be the naming convention that I tend to use for something like that. There's kind of a reason behind that. We're probably going to be creating the next step as we evolve our tools. We go out and buy new sets of Legos, is we're going to be looking at structs, and we're going to be looking at creating classes, object-oriented programming, and we're probably going to name our struct a fraction. And we're probably going to name our class a fraction. So I don't want to steal a name that I might be using soon for something else. So we'll just say the fraction I want to display is the fraction that you passed me.
Can you say green fraction again?
Nope. All right. So for displaying a fraction, this guy is going to, we're just going to display it in some sort of whatever reasonable way. Probably 1/2 is like a 1/2, something like that. So we'll do a cout. The fraction at bucket 0, followed by a maybe a slash like that, followed by the fraction at bucket 1. So now that's display fraction. So now we can call display fraction on F1, and we can call display fraction on F2. Give me a second. I've defined my fraction incorrectly. I've mixed a couple languages together. Okay. So let me show you what's going on here. So I'm going to go ahead. I'm going to call display fraction inside of here. And then we're going to talk about some scope stuff. Rid of those two things. Oh, I also need to kick it down a line, right? Did we look at Endel? Okay. All right, so there's our 1/2 and our 3/4, and I'm printing it inside of my create fraction. We'll talk about why here in a second. All right, so it's giving me some warnings about what I'm returning down here. And this has to do with the nature of how we're creating our array. So inside of here, we have a local variable called F1 that we're using this syntax, what's called the simplified syntax for storing storing an array like this. So we're saying I want a 2-bucket array. Now what this is giving us, so let me just show you a couple of things. I'm going to do a cout F1. What's this going to display? What kind of animal is that going to display if I cout F1? And here I'm actually going to, the better point to ask that question is this. If I say cout F1, what's that going to display to the screen? What kind of value? Go ahead. Yeah, memory address. Okay, because remember, arrays are stored as memory addresses. Yeah, I did some stuff to that array, but what I asked to print out was the array itself. The value of that array is a memory address, right? And we have to go to that array to find where bucket 0 is and find where bucket 1 is. So if I was also going to print out F1 at bucket 0, for instance, then I would get whatever numerator is. But if I just print out F1, I'm going to get a memory address. All right, so we're going to go ahead and do that. And I'm going to comment that out for a second. Then we're going to return F1 in my function. And this guy is going to come out here. And I will see out that guy. Let's get rid of that for now. Keep it as simple as possible. So I'm going to create a variable of type int pointer called f1, and I'm going to call create fraction. Create fraction is going to generate a fraction using this syntax, fill it up with the numerator and denominator, and then locally print out the value of f1, which is a memory address. And then it's going to return that memory address as the return value of this guy. So that's going to be what fires out of here, storing inside this variable called f1. Now we get to the cout. What do we expect to print out there? What kind of value do we expect to print out there? What do you think? What kind of value does that kind of thing hold? Memory addresses? All right, so we expect that to also print out a memory address. Forget about the warnings up here. It's warning us about the problem. So notice inside of, this is a common problem in an older language like C++. So inside of create fraction, when we printed it out, this line right here, we got that memory address. Then we returned that guy. We caught it inside this, presumably. And then we tried to print it out, yet we got a 0. Why? The hint is it deals with scoping rules. And I'm glad we ran into this because this is a super common mistake. And obviously I did it on purpose. I program in a lot of languages each week, so I have an excuse. Go ahead. Yeah, remember when we talked about garbage collection? So newer versions of C++, just like all new languages, have something called automatic garbage collection, which means that as soon as the scope of a variable dies, so remember we talked about pointer counters? All right. And these were all things that we kind of said in passing, but now they're coming back to haunt us. So when I first created this array right here, I got a memory address. So the pointer count of this guy went to a 1. Okay. It used to not exist. Now there's one thing that points to, and it's called f1. At the end of this function, when it's done, what happens to my variable f1? It gets garbage collected, which means the pointer counter goes back down to 0. And when it goes back down to 0, what actually happens? Well, what actually happens is the operating system reclaims it, zeroes it out, and says, oh, I can hand this out to somebody else. That's no longer your memory. So we were completely cool up to this point. We even saw that, yeah, it printed out the right fraction right there. So as long as we were inside of that, function, it knew exactly what we were doing. But when that function ended, the memory that we locally requested in that function, using this particular syntax for creating a fraction, went away. Make sense? So that means we have to look at one of our other syntaxes for creating a fraction, not the automated, quick and dirty way of creating a fraction. And this is, I would call it somewhat problematic in C++, but it does give us an opportunity to talk about this. And we mentioned it already in a previous class. Remember when I had up on the screen that thing malloc, memory allocate? Remember that guy? All right, so in this particular case, we're using a syntax that I like to call this kind of thing syntactic sugar. Syntactic sugar. So this is a kind of a shorthand syntax that makes life a little easier for us. right? Kind of, that feels easier than all that scary malloc stuff, right? The problem with that, though, is this particular syntactic sugar doesn't exactly mimic requesting memory directly. All right. Because what we basically did is we walked into this very temporary plot of land, started digging our own foundation, built some stuff on it, and then after this ended, our plot of land disappeared. So our array was gone. So I would probably encourage you never to use this syntax for arrays. When you go to newer languages like Java, if we were building this array in Java, we would have written it like this. Int array F1 is equal to new int array of size 2. So we're going to talk about this new keyword for a second. It does exist in C++. We're going to call the, and let me show you another. So we're going to say int pointer F1 is equal to the int pointer version of malloc 2 times size of int. Just rolls off the tongue, right? So what's this guy doing? This guy is allocating some memory. How much memory? Well, I need enough memory to hold 2 of however big an integer is. 64 bits, right? Integers are 32-bit values. So this is me fully describing how much memory I need. And that's going to come out of here, as I mentioned before, a void pointer, which is kind of an undeclared pointer. And if it's a void pointer, the default behavior will be, as we're walking through memory, we'll be taking single byte size steps where we really need to take 4 byte size steps to walk from the first integer to the second integer to the third integer. We need to make sure we walk through memory with a big enough gate that we get to the next value. We don't land right in the middle of a number. Okay. So that's why we purposely say you are actually an integer pointer. Okay. That way later on it will behave like an integer pointer. I want to say this might not actually be required anymore since I did set it as an integer pointer here, but my habit is to be specific. This will never be wrong. I am interested for a moment, though, to know if this syntax works in C++, but it actually would be slightly different in here. Oh, actually, I'm going to write it like this. Yeah. Okay. So that syntax. Do we like this syntax better than the malloc one? Feels less cool, though, right? I mean, the malloc one, that just makes you feel geeky. Right, but we'll see. So first of all, let's we're going to move our display fraction. Well, first of all, before I run it again, notice that it got the same memory address inside of the function as it did outside the function. We didn't lose that 0. All right. Why? Because we did not rely on the local environment of our function to request the array for us. We asked for the memory. We bypassed the local scope and said, operating system, I want to work directly with you to find a plot of land that will persist after this function's over. I think I mentioned this probably was several classes ago when we were talking about something about how in the old days with C++ programming, if you had a weird bug in your program, sometimes it would crash your computer because you might write something into memory that was not owned by you and maybe owned by the operating system, and you just broke the current operating system. You would have had to restart your computer to get it to reload itself into memory. Well, now to protect from that, when you run your program, it's run inside of like this protected bubble. Modernly, a lot of times it's called a virtual machine that, and there's lots of actually products that create virtual machines for any sort of application. One's called Docker. that will create a virtual machine to for you to put your entire application inside of, in case that particular application doesn't run inside of a virtual machine by default. Java always runs inside of a virtual machine, and we'll talk about that at some point. But historically, C++, virtual machines were not a thing in C++. So a virtual machine is, think of it as a computer built out of software. And if you run your program entirely encapsulated in that, you basically have your normal computer, your Windows machine, or your Mac, running this other operating system. And anything that happens inside this pod only hurts this pod. It can't get to the outside world. Make sense? All right. So a lot of people in the security industry and things like that, they'll work with virtual machines like that. And also in industry, IT managers will a lot of times, even though you might have a physical computer sitting in front of you, you will actually be on your physical computer opening up a virtual machine so that if anything bad happens to your computer, you know, a virus or something like that, all they have to do is redeploy the virtual machine image, the untouched virtual machine image of your workspace. And now you no longer have a virus and you have all the applications that you used to have installed and things like that. All right. Well, this syntax here predates that idea of a virtual machine. But now modernly, operating systems launch your programs inside of protected memory. So that means that when we asked for our array using this syntax in here, that was protected memory that was reserved specifically for this function. And that protected memory disappeared at the end of this function because it was a local variable of this function. This is no different than if I had defined an int a is equal to 5. At the end of this function, that variable a is gone, right? And if I had returned that variable a, the reason I would have gotten the 5 out someplace else, right? So let's just see that. If I say I'm going to return an int, I'll just delete this stuff. I'll go ahead and return a. Up here, I will go ahead and capture that a. So don't pay attention to my variable names here. So I'm going to create an integer named f1. We're not even dealing with fractions right now. So I'm going to create an integer f1. I'm going to call create fraction. Doesn't actually matter what I pass in right now. It's going to just define a local variable name a of type int, and then return that value. Now, what we saw a few minutes ago is if I had done this using the old array syntax, this guy right here, and here we'll just to keep it completely the same. I'm going to print out the 5 here, right? And it's still going to be a 5, just like when we printed out the array, we got the memory address. Then I'm going to return the a, which is going to fire out of here. We're going to catch it inside of this variable. Then I'm going to print it again. Remember when we did this with our pointer, our memory address, we got a 0. We didn't get the same memory address again. What are we going to get with this integer? What's the value of a? 5. So we're going to, what did I do? Oh, it's because I still had this set up as a pointer up here, except not that one. It's this one. My prototype still had it returning a pointer. So now I got 5 both times instead of a 5 and a 0. Why is that? Based on what we've learned, when we returned this a right here, it was using the same mechanism as pass by value, right? So we passed a copy of the contents of a, the 5. A still disappeared after this was gone, but I handed out a copy of it. Whereas if I use this syntax and I was returning an int pointer, this guy, F1, F1. There's a pointer. Int to int pointer. Oh, that guy, not that guy. All right, forget about the warnings. It's the same warning we talked about before. So this is effectively identical code that I had for the integer, but now I'm working with our fraction syntactic sugar, and I got the right kind of memory address inside, but outside, because I was returning the memory address, I was passing by address. Because I was returning a memory address, it passed the address where the value would be. Yet when that function ended, that address was reclaimed by the operating system, which is why the pointer now holds a 0. All right. So I need to be the one in charge of creating my memory. So if I do nothing different here, except get rid of that guy and write it like that, I could say I want to generate a integer pointer named F1, and I want to build it as an integer with 2 buckets, but I'm going to use the new keyword, which is really the newfangled version of malloc. So the new keyword new is like our real estate agent that we ask to go find us memory, and it negotiates with the operating system to find the right size plot of land place in memory. All right. So ultimately, it's going to get us the same structure as we had before. But instead of creating it as a local variable that dies off when it's done, we are working with more global memory by talking directly to the operating system. We're not bypassing that by using the local function that's going to die off at the end of this as an intermediary. And it's because pointers are passed by address. Integers are passed by value. Passed by value means send a copy. Passed by address means send the real thing. And we got the 0 because the real thing changed after this function ended, right? But now, if I define my array that way, where I'm asking for the memory, I'm saying, real estate agent, go find me some stuff. How much stuff? Enough stuff to hold this many of these guys. And this is the exact same syntax as we have down here. It's just better syntactic sugar than this one, right? Not quite as friendly as this one, but definitely, if you always create your arrays this way, you won't ever run into this issue, because you are always responsible for the memory, which then means when you're done using that memory, you're also technically responsible for cleaning up. We talked about last time, right? Even though most of the time we just rely on automatic garbage collection to clean up our messes, and who cares? It's computer's problem. Not great programming practice, but common programming practice. All right. So we'll go ahead and generate our array. I'll leave this other syntax in here just so you see it. We'll set the numerator and the denominator. Then we'll return it. And now we can say display fraction F1. and we get our 1/2. Similarly, if we want to get our second fraction, F2, we want this guy to be 3/4. And then we display F2. Now we'll get our 3/4. Make some sense? So this is similar to that plus plus operator thing where I said it's never wrong to just put it on its own line. If you want to increment the value, A plus plus versus plus plus A, they do have different behaviors, but the ultimate result of it will always be identical if you always put them on a single line by itself and not try to embed it inside of the rest of your code, just because you think saving one line is cool. Every now and then you will run into an example where it does actually benefit you being able to inline it inside of a function, especially when you need the current value and then but you do want it to then change. But that's once in a blue moon, and that's something that you'll have a lot more programming experience before you run into problems with that. All right. Where's my rest of my... All right, so I did create fraction, I did display fraction, so now we need to do add fraction. All right. So add fraction is going to return an int pointer. We're going to call this guy add fraction, and it's going to take an int pointer f1 and an int pointer f2 for our two fractions. If I'm being consistent, I'm going to call it fraction 1 and fraction 2 to really spell it out. Go ahead and write this guy down here. All right. So we know we're going to be generating a brand new fraction, right? That we're going to be returning. So when we're representing fractions as 2-bucket integer arrays. So we'll say int pointer answer is equal to a new int of size 2. Ay, ay, ay. So that'll generate me memory that I own that represents an empty 2-element array. All right. So now what we'll do is we need to actually add the fraction. So if I had the fractions 1/2, oh my gosh, you're killing me. How about not complete it? If I have the fraction 1/2 and I had the fraction 3/4, this is trying to complete that. If I have those two and I want to add them together, what do I have to first do? I have to get a common denominator, right? Okay, this is going back to when we first learned how to add fractions, which has been a couple of minutes probably. How many of you had to Google it? Don't want to admit it. I think most of us would have had to Google it at some point because it's not something we deal with very often, right? It's not that it's hard, it's just collecting dust in the back in the back of the warehouse somewhere. All right. So usually a good way of starting off by getting a common denominator is just multiply the denominators together, right? So I would have a common denominator of 8 here. So this would actually become 4/8 and 6/8. So 2 times 3 is 6. 4 times 1 is 4. 2 times 4 is 8. So now we have 4/8 plus 6/8, which is going to give us We add those together, we're going to get 10 eighths in that example, right? So we want to mimic those operations. All right. So in our answer, in fact, let's actually just put it in separate variables. We're going to say int new denom is equal to our two denominators multiplied together, right? How did we get our 8, our new denominator? We multiplied the denominator of these first two together. So that is fraction 1 at bucket 1, that's the denominator from that fraction, times fraction 2 at bucket 1, the denominator from the other fraction. All right, so we get those multiplied together, so now we have our new denominator. Our new numerator will be equal to fraction 1 at bucket 0 times fraction 2 at bucket 1. So we cross multiply there. So we get that answer plus fraction 2 at bucket 0 times fraction 1 at bucket 1. So this updates the first numerator to be compatible with the common denominator. This updates the second numerator to be compatible with the common denominator. We add those two guys together, and that's our new numerator. Finally, we put inside of our answer at bucket 0 is equal to new numerator. Answer at bucket 1 is equal to new denominator. And then we return the answer. So now up here, I can say int pointer f3 is equal to add fraction f1 comma f2. And then I can say display the fraction f3 which is our 10/8. Make sense how we did that? We solved it as a normal person, collecting our steps, and then mimic those steps in code. That's the way for a long time you're going to have to be solving your problems. And really forever. As the problems get harder, you'll have to write more stuff down. You'll be able to do less visualization inside your head, but it's never wrong to do this, right? This is the step. This is what I had to do to find a common denominator, multiply the two denominators together. This is what I had to do to add my fractions. I had to update the two numerators and then add them together. Update them based on the new common denominator. Then I set my numerator and denominator in my answer and ultimately return the answer. Okay, so we get our 10/8. Questions about that? Keep in mind that I can pass it any values here. And it still works. It doesn't just work for 10/8. Okay, so now we have generic functions. We have a generic function for building a fraction. We have a generic function for displaying a fraction and a generic function for adding two fractions. All right, so now we're supposed to write reduced fraction. All right, and this is the one that gets fun. Because the algorithm we're going to use, the algorithm I'm sure most of you used, is just a brute force approach, right? Let's just find the biggest number that divides both of them. It makes sense. right? Any reasonable person would think that that's the perfect way of doing it. Computers are super fast. Who cares? We'll just zip right through them. And okay, so let's go ahead and write that. So we have int pointer. Actually, we could really make a choice here. And I didn't specify, I don't think, in the assignment. Oh, I did. I said in the original memory. Okay. So we could have made a choice. We could have said, I really want to return a brand new fraction that is the reduced version of the fraction I passed in. That way you still have the unreduced version and the reduced version. But instead, in this case, I asked you to do it in the original memory. So effectively what we're doing is we're zapping the original one to be its reduced form. Okay. So this guy is not going to return a value because I'm just going to change it inside of memory. It's going to be called reduced fraction, and it's going to take an int fraction, the fraction, I'm staying consistent, right? As a parameter. Let me take this gap out of here. All right, so here's our reduced fraction. All right, so to reduce the fraction, we need to find the biggest value that evenly divides both the numerator and the denominator. So maybe as a starting point, we might start off with what is the largest value that possibly could evenly divide both the numerator and the denominator? It would be the smaller of those two values, right? So I can try to be a little bit efficient, right? And say, well, I'm going to find the smaller of the two values. So I won't check things that are just impossible to evenly divide them. So let's find out what the smallest value is. So I'll say int smallest is equal to, I'll just make an initial guess. We'll say that the numerator is the smallest value. All right. Then I'm going to ask the question to find out if I'm wrong. If the fraction at bucket 1, if the denominator is actually smaller than smallest, I'll go ahead and update my variable smallest to the denominator. So assume that the numerator is the smallest, then ask the question, is the denominator actually smaller? If so, update my memory so that I now smallest will hold the smaller of the two values. Make sense? All right. So now what I want to do is I want to do a countdown. Now we know that both of those numbers will be evenly divisible by 1. In such case, it's already reduced, right? Okay. But what I'm going to do is I want to start a countdown. I want to try every single number from smallest all the way down to 1 until I finally find a number that evenly divides both the numerator and the denominator. Since I'm starting at the maximum number it could possibly be, the first number I hit that evenly divides both is the largest common divisor, right? So we're going to start a for loop for int I is equal to smallest. Keep going as long as I is greater than or equal to 1. You can say greater than 0 as well. I happen to know that this is going to end at 1 anyways, right? I'm not getting past 1. They're both going to be evenly divisible by 1 because that's how math works. But it's not going to be a problem for us here. And then we're going to say I minus minus. Or minus minus I. Either one will suffice in this case because that's happening on its own. So we're going to ask a question. If the fraction at bucket 0, when divided by the current value of I, has a remainder of 0. Now, if you didn't want to use the complex operators, you could have put another if statement inside of here. You could have said, if the fraction at bucket 1 is also evenly divisible by 0. So really, I'm asking two questions. If the numerator is evenly divisible by I, then let's check the denominator. If the denominator is also evenly divisible by I found my answer. So I'll go ahead and say the fraction at bucket 0 is equal to the fraction at bucket 0 divided by the current value of I. The fraction at bucket 1 is actually equal to the fraction at bucket 1 divided by the value of I. I would only be inside this if statement if the numerator is evenly divisible by I and the denominator is evenly divisible by I. Make sense? Now, you could have done the double whammy here. I don't think we've actually talked about these operators because I went a little bit out of order to get us to the point for the quantum stuff, but you could have used the AND operator and said, if this is true and this is true, then do this. So and is double ampersand, or is double vertical bar. Not to be confused with that and that. A single ampersand and a single vertical bar are not syntax errors. Those are actual operators. Anybody know what the operators are? We have bitwise operators. A single AND is the bitwise AND operator. A single vertical bar is the bitwise OR operator. Perfectly self-explanatory, right? All right, so as a quick example, if I have the number 7, and I'm going to bitwise AND that with a 3, what I'm actually doing is I'm going to have to look at the binary version of 7, which is 111, the binary version of 3, which is 011, and then on a bit-by-bit basis, I do an AND. 1 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, so the answer of this guy will be 3. You will rarely use this in normal business programming, but it is quite useful when you deal with things at a lower level, or like masking IP addresses for subnets and things like this. So it is useful, just not for normal stuff. Okay, but what can be frustrating for a programmer is the very first time you accidentally use a single AND instead of a double AND, it doesn't scream at you. You just get a numeric answer rather than a true and false. And if that numeric answer happens to be, well, since the way Booleans work in an older language, a 0 is false and anything not 0 is, or 0 is true, anything not 0 is false. So it'll work as a Boolean, which then makes debugging terrifying, right? So keep that in mind. The OR works the same way. An OR is one or the other or both. So this would be 111. So if I had 7 or 3, it would be 7 in that particular example. All right, so from a studying perspective, that's more of trivia information. I'm not going to test you on that in here. You'll probably see that more in your 325 class when you kind of talk about how things work at the lower level. But it really isn't difficult. You just have to know that those operators are not the same. Okay, so and one of them is a mathy thing, the other one's just a Boolean question thing. So I would say 99.9% of the time when you're writing applications and you want to say and, you'll use the double ampersand. It's the same syntax in C#, it's the same syntax in Java. In Python, it's just the word and, or the word or. Doesn't matter, all means the same thing. Python has bitwise operators too. It just spells it out a little bit better. I think it's called, maybe it's even called bitwise and, I don't know, but so we'll give Python the win in that one, that they at least don't look alike. They're very prone to typos. All right, so if both the numerator and denominator are evenly divisible by both of those guys, we'll update this and then we'll return. Remember, return makes the function immediately end, right? I don't need to check any additional numbers. I have, since I started at the biggest number possible, and I started counting down, as soon as I find one that evenly divides both, that is the biggest number that evenly divides both. So I'm done. Return. Remember, return makes a function immediately end, and then you can optionally return a value. Not in this case, though, because we advertise that we're not returning a value. Okay? Which means that I don't have to deal with the second return down here. If I never get into this if statement here, if that never happens, my function will die a natural death and I will not have made any updates to the to my fraction. In fact, you could optimize this a little bit and basically say greater than 1. We don't actually need to check 1 because we know 1 will evenly divide both of them. And we are wasting our time doing the math of dividing something by 1, giving us the original value. But it didn't hurt anything, but we can take that out. All right, so now what we can do is we can call reduce fraction on F3 and then display fraction on F3 after we reduced it. I need to spell see, I always test people for when I make typos, and nobody yelled at me about this. No star for the day on that one. It was an obvious, it was a layup. All right. Well, here, let's give us the friendlier numbers. It worked, but let's give ourselves friendlier numbers that we can conceptualize. So we have our 3/4. So there's our 10/8 reduced to 5/4. Make some sense? All right. Does that answer all the display? Okay, so that's the answer to the homework. I'll save that. I'll share that. All right, so you have that. In my last couple minutes here, let me just start transitioning to what we're going to talk about on Thursday, still with this code. Because right now, we're pretty convinced that this works. No problem, right? Well, let's get to some bigger values. So let's do, that's 200,000. That's 2 million, 20 million, 2 billion, which does fit inside of an int, right? And we'll call this guy, I'm just gonna randomly put some stuff in here. That's 1 billion something or other. And that's 2 billion something or other. Okay, I just so it all fits, I'm gonna purposely give them both the same denominator. All right. Now, we will currently have a problem, though, because right now we assume that they do not have the same denominator, right? So we'll multiply them together, giving us a value that doesn't fit inside of an int. So just to quickly show this, I'm going to update my add fractions a little bit and just say if fraction 1's denominator is not equal to fraction 2's denominator. So if they're not equal, then let's update this thing and to get our new denominator. All right. And since we're out of time here, I'm gonna interject an error into my code. Finish this for not updating denominators when they are the same. So effectively, what I'm going to start off by doing the first couple minutes of next class is I'm going to generate something that gives us a couple of large fractions. Actually, this isn't going to work anyways. I'll have to make my numerator and denominator a little bit smaller because I need to make sure when I add them together, they're under 2.1 billion. We'll update it to a long anyways to really drive the point home. But what we're going to see though is once we do that, once we allow our fractions to get scary looking, we'll see that our reduced function still functionally works. But if you're starting at a number like 2 billion and you're counting down towards 1 to find the greatest common divisor, it's going to take a few minutes. Okay, I think that'll probably take a couple of days. If we go and work with longs, we're counting down from what, 9.3 quintillion? A little bit longer. Then we can get into most languages have arbitrary size integers if you that are built in classes that allow us to just have any size number where the performance will keep degrading as we try to hold ridiculously big numbers. So we're going to see that this is a time complexity problem where this will not finish in a reasonable amount of time, yet everything we did today was reasonably easy math, right? All right, so we'll look at that at the beginning of class on Thursday. And then, oh man, we're going to have an impossible assignment over the weekend. So I would just clear your schedule. I don't think it'll be any worse than your other ones. Maybe that still means an impossible assignment, but.